Hi, I'm Braden Mariconi, and this is Lab 2, Charge Tapes Revisited. In this lab, we improved our original charge estimate by modeling each tape as a line of many point charges instead of a single point charge. Introduction. In Lab 1, we treated each tape as a single point charge to estimate the net charge. However, in reality, charge is distributed along the entire length of the tape. So in this lab, we built a computational model in GlowScript where each tape in my computational model was 20 evenly spaced point charges. This better represents how electric forces actually act between tapes. Using the same measurements from lab 1, we calculated a new charge value of 2.1417 times 10 to the negative 8 coulombs. This lab, this is our experiment diagram of how we got the charged tapes. And here are some of the materials we used. Some of the key concepts was that this lab relies on Newton's second law. Force determines motion. Since the hanging tape is stationary, the net force on it must be zero. Coulomb's law. The electric force between two charges depends on the product of the charges and decreases with the square of the distance. The superposition principle, which we use to calculate the electric field or force from each small charge individually and then add them together as vectors. And equilibrium, because the hanging tape does not move, the electric force upward must balance gravity downwards. To simplify the model, we made a few assumptions. One, that the charge on each tape is uniformly distributed. We ignored air resistance, and that both tapes have equal magnitude of charge. Looking at the free body diagrams of the hanging tape, there's a downward force from gravity. There's an upward electric force due to the held tape. Because the tape is in equilibrium, those forces must be equal in magnitude. So mathematically, electric force equals gravitational force. That relationship allows us to solve for the unknown charge. In lab 1, when we treated the tape as a single point charge, we found 3.2618 times 10 to the negative 9 coulombs, assuming that the entire tape charge was just a point. In lab 2, using the distributed line of charge model, we found 2.1417 times 10 to the negative 8 coulombs. This difference occurred because the point charge model oversimplifies the geometry. When charge is distributed along the tape, the distance between the individual charge elements matter, and that significantly changes the total force calculation. The line of charge model is more realistic and therefore more accurate. These are our constants for the computational model. We first defined the physical constants, and we inputted the measured masses and estimate charge. Next, we defined functions for the electric field based on Coulomb's law. Then we construct each tape as 20 small charged spheres evenly spaced along its length. This converts a continuous charge distribution into a sum of discrete point charges. After calculating the electric field at each charge, we multiply by charge to find force. Then we sum all those forces to get the total electric force on the top tape. We compare that to the gravitational force, which is simply mass times g. The white arrow represents the net electric force, the yellow arrow represents the gravity. When their magnitudes match, the system is in equilibrium. There are two main sources of potential error. Sorry. There are two main sources of potential error. First, imprecise measurements, especially tape separation and alignment. Second, charge loss. Handling the tape can cause charge to dissipate over time. However, and both would affect the force balance and therefore change the estimate. If we treat the tape as a point charge, we get a much smaller value. When we model it as a distributed line of charges, we get a larger, more realistic value. The difference highlights the importance of modeling assumptions in physics. A more accurate representation of geometry leads to a more accurate calculation. The final result of 2.1417 times 10 to the negative 8 coulombs reflects a model that better matches the real system. Thank you for your time.